Enthalpy and enthalpy of reaction. The word enthalpy is derived from the Greek noun enthalpos, which means heating. Enthalpy, and we use a capital H, is defined as the internal energy of a system plus the product of pressure and volume. And the three horizontal lines there mean it's a definition. E is the system's energy, V is its volume, and P is its pressure. It is not possible to measure enthalpy directly. Only the change in entropy, or delta H, can be measured. So the enthalpy equation becomes delta H is delta E plus delta of PV. We will only be measuring enthalpy under conditions of constant pressure. So we can take the P outside of the delta there, and we have delta H equals delta E plus P delta V. Let's now compare the enthalpy equation to the change in energy delta E of a gas under constant pressure. Please note Q sub P is the heat at a constant pressure, and W is the work done by the surroundings on the gas. The subscript P in Q sub P is not always shown, but it is implied when dealing with enthalpy. So here's delta E is Q sub P plus work. And then what do we do here? We have a negative sign here. That's due to the fact that when a gas expands, your delta V, your change in volume, is positive. So the gas's energy decreases, which means you get a delta E that is negative. We then rearrange the equation to solve for Q sub P. We bring over the Q sub P equation from the previous slide along with our definition of enthalpy. The right sides are the same. That enables us to say delta H, or change in enthalpy, is Q sub P. So the change in enthalpy at constant pressure, and that's the only one we're dealing with here, is the heat lost or gained by a system as a reaction occurs, which is why it is also called the enthalpy of reaction or the heat of reaction. If a process takes place at a constant pressure, the work is due to a change in volume, and the enthalpy change for a system is equal to the heat. At constant pressure, the change in enthalpy of a system is the heat lost or gained by the system as a reaction occurs. Note that the change in enthalpy differs from the change in energy only because of the work done by a change in volume. For systems in which the volume is constant, the change in enthalpy and the change in energy are the same. Very often in chemistry, we classify properties of matter as intensive or extensive. Intensive properties are those that do not change with the quantity of a substance. Color, hardness, density, freezing point and boiling point, and temperature are all examples. For example, if we have 100 milliliters of water and we remove 5 milliliters, the temperature of the 5 milliliters of water will be the same as that of the remaining 95 milliliters of water. Extensive properties are those that do change with the quantity of a substance. Mass and volume are examples. Using the prior example, if I have 100 milliliters of water and I remove 5 milliliters of water, the mass of the 5 milliliters of water will not be the same as that of the remaining 95 milliliters of water. Intensive and extensive properties can also be applied to thermochemistry. Enthalpy is an extensive property. Its value depends on the quantity of the substance that reacts. So let's say we combust 16 grams, that is 1 mole of methane. In that case, the change in enthalpy will be negative 891 kilojoules. But what if we combust 2 moles of methane? In that case, the change in enthalpy is twice the amount of enthalpy change for 1 mole. So that would be negative 1,782 kilojoules. The magnitude of the change in enthalpy is directly proportional to the quantities of reactants and products. If the coefficients are multiplied by an integer, delta H, change in enthalpy, is multiplied by that same integer. So in this case here, how many moles of methane do you see? Well, just one. There's an understood 1 in front of the CH4, So the delta H will be minus 891 kilojoules for that combustion reaction. The change in enthalpy for a reaction also depends on the phases of the products and reactants, since the enthalpy of a substance differs depending on whether it is liquid, solid, or gas. Once again, let's look at methane. When we combust methane here with a gas and a gas of oxygen, and we produce gaseous carbon dioxide and gaseous water or water vapor, we have a change in enthalpy of negative 891 kilojoules. But what if the combustion results in, once again, gaseous carbon dioxide, but this time liquid water? Then the change in enthalpy is negative 979 kilojoules. The enthalpy change for the second reaction is more exothermic. The magnitude is greater than the first because when water is converted from a gas to a liquid, energy is released. The change in enthalpy for a reaction in the forward direction is equal in size or magnitude, but opposite in sign to the change in enthalpy for the reverse reaction. So here's our first reaction. We're combusting methane. Delta H there is negative as heat is transferred out of the system. We have a negative Q sub P, so delta H is negative. The second reaction is the reverse reaction. In this case, we have water plus carbon dioxide gives us methane plus oxygen. This case, it requires a transfer of heat into the system to occur. We have a plus Q sub P, so delta H is positive. Here's a pictorial version of it where we are combusting 1 mole of hydrogen with half a mole of oxygen. In that case, delta H is negative, it's less than 0, and you form liquid water. So you have a decrease in enthalpy. Now, if we go the reverse reaction, where we decompose water into hydrogen and oxygen, we have the same magnitude, but the opposite sign. So delta H going up is positive. It's greater than 0. We've already stated that the change in enthalpy is equal to the heat transfer, Q sub P. So Q sub P and delta H always have the same sign. So we have an endothermic process. That's when delta H is positive. Right here, we've got a plus Q, heat's coming in. So delta H is greater than 0, as is Q. That's an endothermic reaction. We're exothermic when delta H is negative. So here, delta H is less than 0. Heat is negative Q, which means it's being transferred out of the system to the surroundings, exothermic reaction. While enthalpy change is an extensive property, enthalpy change per mole, big difference, we're dividing it per mole, that is an intensive property. This means that for a given reactant in a reaction, regardless of the amount of reactant is used, the enthalpy change per mole will be the same. Let's plot an energy profile diagram, and we're going to plot enthalpy over process of reaction, where that's basically a function of time. The difference in enthalpy between the reactants and the products is shown for both exothermic and endothermic. For exothermic reactions, delta H is negative, right? The reactants have an energy up here, an enthalpy here, and they wind up with a lower enthalpy. And this is the activation energy to get the reaction going. For endothermic, the reactants have an H here, an enthalpy here. We have a higher enthalpy at the end with the products, so delta H is positive. That's endothermic.